In the previous lecture, we started the discussion on developing a comprehensive small signal model for the MOS transistor. So now, having done that and armed with that knowledge, let us see if we can develop the bandwidth of a MOS transistor. So what do we mean by bandwidth? Well, in general, bandwidth refers to a range of frequencies over which we say that the device or a circuit actually works. But that is a very loose definition. We don't actually define what we mean when we use the term working. So usually what happens is, let us say for circuits like amplifiers or filters, we refer to something called as a 3 dB bandwidth, or the bandwidth or those frequencies where the gain in terms of power essentially becomes half, or half of the maximum possible. So even with respect to the MOSFET, we can actually define what we mean by the bandwidth. So generally, when we are talking of the bandwidth, we expect that the response will be low pass. This is the expected response. And that is not a wrong thing to expect, because as you know, at very low frequencies, the capacitances inside the MOSFET don't play a role. So therefore, it is able to give some gain, and at higher frequencies, those capacitances become more and more dominant and would definitely cause the gain to come down. So having said that, let us define what we mean by the bandwidth. So since we are talking of a low pass response, there is no need to talk of a bandwidth. All we need to talk about is any one frequency on the upper side. So what we define is something called as Ft. That is also called as the transition frequency. And that transition frequency is defined as that frequency where the small signal current gain of the transistor becomes 1. So therefore, if I define the y-axis as something like I out by I in magnitude, then the frequency where the gain essentially becomes 1, that is called as Ft. Now you may question that how can we define current gain, or rather how can we define the input current of a MOSFET? A MOSFET does not draw any current at the gate. Well, you are right, it does not. But now we should be able to be in a position where we know that the DC current drawn by the gate of a MOSFET is 0, but the AC current could be non-zero because of the capacitances. So therefore, when we define the small signal current gain, what do we mean? This is my MOS transistor. Let us say I give some AC input over here, that is called as I in. The body of this NMOS is connected to ground, and I define my I out as the drain current. So when I say the small signal current, it means that all the DC sources in the circuit must be deactivated. So therefore, both drain and source DC sides, I'm connecting them to ground. And I define that my current gain, or AI, is equal to I out by I in. Notice that the currents, I have labeled them in small letters, indicating that they are small signal or AC currents. So therefore, let us put the small signal model of the MOSFET over here. So let us start from left. We have the current source I in. Then we come to the gate of the MOSFET. So there are two devices essentially, two capacitances. One is the CGS, one is the CGD. And this is the gate, this is the drain, and this is the source. As you know, there's a current GM VGS, where VGS is essentially this voltage. Then in parallel, we have the RDS. And then the drain is also at AC ground. So therefore, this is what we can show. The other current source GMB times VBS will not play a role because both the body and the source are at AC ground. So therefore, that will not really have any difference. Similarly, the body capacitances with respect to the drain and the source would not play any role, again because all the terminals are at AC ground, the drain, source and the body. So our model essentially reduces to this. So effectively what we are seeing is that because the drain is at AC ground, this point is at ground. So therefore, because even this point of the CGS is at ground, we can say that effectively CGD and CGS are like in parallel. And we can define that if I in is over here, the I out is essentially flowing into the drain and coming out at the source. So let us quickly redraw this circuit diagram to make it a little bit more simple. We have I in. We can put the two capacitors in parallel and say that this is one big capacitor, CGS plus CGD. And this is GM VGS. This is RDS. The drain is at ground and this is I out. And this is obviously VGS. So therefore, let us try to develop a relationship between the I out and the I in. Let us try to solve for VGS. So VGS will be this current multiplied by the impedance of this capacitor. So the impedance of the capacitor is 1 by j omega times the capacitance. So multiplying that by the current, we get I in by j omega CGS plus CGD. And I out, what will be I out? I out will be nothing but GM times VGS, because this current source has two paths to go. One is to ground and the other is through the resistance. So obviously it will choose to go to the short circuit path. So I out is nothing but GM times VGS. We already know what VGS is. So therefore we can say I out is GM times this quantity, that is I in, divided by j omega CGS plus CGD. So we have I in and I out on two sides of the equation. That means the current gain AI, which is I out by I in, is nothing but GM divided by j omega CGS plus CGD. So what we are interested in is the magnitude of this current gain and when it becomes 1. So if mod of AI is 1, then I can say GM, then the mod of this will be GM divided by omega times CGS plus CGD, that will be equal to 1. So at that frequency we can say omega will be omega t. At that frequency, when the current gain becomes 1, omega will be omega t, or the transition angular frequency. So therefore I can say that omega t will be GM divided by CGS plus CGD. So what we are essentially looking for is the FT, or the unity gain frequency. So therefore, as you know, Ft is nothing but omega t by 2 pi. This will be Gm divided by 2 pi times CGS plus CGD. This is called as the transition frequency, also called as the unity gain frequency. So if you know the transconductance of this transistor, and also you know the gate to source and the gate to drain capacitances of the MOS transistor that you're working with, you can calculate the unity gain bandwidth quite easily. Now, for RF transistors, we would want that this Ft should be as high as possible. But one thing to note is that if somebody is trying to sell you a transistor, saying that the transistor that I'm selling you has an Ft of, let us say, 15 gigahertz, don't fall easy prey to that statement. Why? Because this Ft is more of an idealistic quantity. Why I'm saying this is idealistic is because we have calculated this only for the MOS device. And when we are using that MOS device to make other complex circuits such as amplifiers, there will be other elements also, which may further bring down the bandwidth. So therefore, you can definitely know what the Ft is, but don't expect that in reality you will get bandwidths like that. And more importantly, this is something where you get unity gain, that too with only one device, no additional circuitry whatsoever. So therefore, this is more of an idealistic quantity and it is used as a ballpark estimate. So the point is that you can definitely refer to it, but don't consider this as a rule of thumb that high Ft means it's a good transistor and it will work until that frequency. In practice, no, that's not the case. In reality, you can consider yourself lucky if you will get the transistor to give you proper gain at even half that frequency. So all said and done, the Ft is not something that you trust so easily, but at the same time, it is not something that you can completely disregard. If the transistor has extremely high Ft, it's a good idea to take it, especially if you are planning to work at frequencies which are way below the Ft. So let us say if a transistor has an Ft of 25 gigahertz, you can expect it to work pretty well up to at least 5 or 6 gigahertz, if not more. So if your application is in the area of 5 to 6 gigahertz or less than that, you could definitely consider taking the transistor which is offering you an FT of 25 gigahertz. So if I want a transistor with high FT, what can be done? So for high FT, one way to do it is increase the GM. But GM is something that is controlled by the circuit. What is the factor that is controlled by the technology? It is CGS and CGD. So if you want to have high FT, CGS and CGD should be low. And that happens, that is CGS and CGD become low only when your device keeps getting smaller and smaller. When the Mosfet transistor is scaled down more and more. So smaller the transistor size, more will be the bandwidth. So therefore, scaling down for MOSFETs, as we have been mentioning in the last lecture or so, is not a bad idea. Although it is not as simple, there are some tricks also. It's not as though you can keep decreasing the size of the transistor and expect it to work just the way you want it to. That's also not 100% correct. But indeed it is true that if you reduce the size of the transistor, its unity gain bandwidth increases. Now, having defined what is Ft or omega t, there is one more quantity we defined that is a little more realistic. We said that the Ft is somewhat of an idealistic quantity. So more realistic quantity that we define is something called as F max or omega max. And that is the frequency at which the power gain of the transistor becomes unity. The AC or the RF power gain. Or what we call as the usable power. So therefore, suppose we are biasing the MOSFET in such a way that it is able to consume some power at the input and it's able to deliver a power to a load. So it's like saying I have the MOSFET over here. Let's say I'm biasing it in such a way that, let's say this is VDD. I'm biasing it with the current source. And this side is connected to ground. And I'm giving some RF input over here of some power. And let us say I wanted to deliver this power to some load RL. Let us say for the purpose of analysis, this capacitance is very, very large. So it does not play any role in offering any impedance at a very high frequency. So at very high frequency, this almost acts like a short circuit. But at DC, this is able to block. So this DC blocking capacitor does not play a role. So therefore, we expect that some AC power should be delivered to this load. But at the same time, there should be some usable power or active power that should be drawn by this MOSFET. But here there is a problem. The problem is that the input stage of the MOSFET is largely capacitive. There is no resistive element over there. So therefore, only for this sake of discussion, we introduce something called as the gate resistance or RG. Resistance of the gate material. The gate material is nothing but polysilicon. So therefore, what we do is that we assume that there is some resistance over here. So when we draw the small signal model of this equivalent circuit, we will say this is the input. There's a small gate resistance, we will call it as RG. Here it is CGS. This is VGS. Then comes CGD. And this current source now does not play a role because it's DC. And the VDD is also replaced by a short circuit. Then we have the GM-VGS. Then RDS. And finally, this is a short circuit, so we directly have this RL. So what we assume is that if this is V in, let there be some current over here called I in, and some current I out is at the RL, and here we call this as V out. So input power is something like V in times I in, and output power is I out times V out. So the analysis is doable, although it is pretty lengthy, and the reason for that is the CGD. So this one is what makes the analysis a little difficult, but I'll give you a hint in the way you can start this analysis. What you notice is that here at this junction with respect to ground, the voltage is VGS, and over here it is V out. The nature of the device is such that if there's an increase in VGS, there's a decrease in V out. So therefore, this capacitor CGD is connected across 2 points which are sort of opposing in nature. If one increases, the other reduces, and vice versa. So therefore, you can use the Miller effect and you can essentially transform this capacitance in parallel with CGS using the Miller's theory. I leave that to you as an exercise. And then you can calculate what's the power that's being delivered to this resistance, gate resistance over here, and what is the power that is delivered to the load, and the frequency at which that happens, or the frequency at which the power gain, the active power gain essentially becomes 1. That is the frequency we are looking for. That is the omega max or F max. So what we see after this analysis is omega max is almost equal to, as an approximation, it almost comes out to be half of the unity gain angular frequency divided by this RG times CGD. So from this you can actually find out F max, which is nothing but omega max by 2 pi. So the two frequencies that we saw, one is the unity gain or the transition frequency, the other is the unity power gain frequency or the F max. So this Ft and F max, they are called as the figure of merit for an RF transistor. So you can see, you can take different cases and see which one is more, whether Ft is more or Fmax is more for a given transistor. I leave that to you as an exercise. Now, as I was saying, it is not sufficient to know the bandwidth of the MOS device only, because in reality it is not the device which is supreme. To make an amplifier or any other RF circuit, that MOS transistor has several other elements: biasing circuits, other capacitances, loads. So therefore all of these have the potential to affect the bandwidth of the whole circuit, and at the end of the day we would like to see what is the bandwidth that our whole circuit can work over, not just the transistor. So therefore we need to see whether the circuit that we have made or the circuit that we have in front of us can give us the desired bandwidth. So one of the ways to do that is to sit down with the circuit, convert it into its small signal model, and find out the gain expression as a function of frequency, and then see at what frequency the gain is becoming 1 by root 2, the voltage gain, and that's your bandwidth. But not all circuits are so simple. There are many complex circuits where this analysis would take a lot of time. In that case, one thing that we can do is simulations. Then again, not everybody is so lucky to have access to a good RF simulator. They are extremely costly in general. So therefore, there should be some techniques through which we can arrive at a quick estimate of the bandwidth. The word estimate over here is important. So therefore, what we are essentially trying to do is that we are merely trying to estimate. That means we don't want to know the exact bandwidth, but we want to know a figure that is pretty close to what the actual bandwidth is. So the question is, can we quickly estimate the bandwidth of a Mos amplifier RF circuit? The answer is yes. So one of the techniques that we are going to look at today is that the technique is called the method of open circuit time constants. So open circuit, what it means we shall see very soon. But time constant, as you know, refers to the product of R and C in general, or if you recall your knowledge of transfer functions, the H of S, so to speak, the time constants are an important part of that. So essentially, the method of open circuit time constant works for two cases. You can only use it when, these are important. First one, that the H of S or the system transfer function should consist of poles only, no zeros. Okay, no zeros. As you know, poles and zeros can form a part of any transfer function in general. The second technique is that the poles should be real. These two are extremely important criteria. Okay. So for the poles to be real, you will need to have only inductors or only capacitors in the circuit, but not both. Otherwise, what will happen is that you will get a second order term and the root of that will be a complex root. So, one good thing is that in most of the RF circuits with using Mosfets, the chances of inductors coming in the middle part of that circuit or in the core part of the circuit is very less. It is majorly capacitive. So therefore, this one is achievable. Now let us see how to work with this. Now suppose somebody has given you a Mos amplified circuit. In general, it may look like this. Let us say you may have some capacitances that are inside, some capacitances that are outside. So let us say I have one capacitor that's outside over here. Then there are capacitances which are inside the MOSFET. Let's say this is VDD. Let's say this is the DC I bias. Let's say one more capacitance I have over here. Let us say this is ground and this is a load capacitor. So let us say there are so many capacitors. This is input, this is output. So let us say this is C1. Let us say there are n number of capacitors in the circuit. Let's say this is Cn minus 1 and this is Cn. All the rest of the capacitors are inside the MOSFET. Just we'll assume that. So effectively what we are having is a circuit that makes use of n number of capacitors. So we have C1, C2, C3, C4 all the way till Cn. Now the way to go forward over here is this. Now comes the fun where we will actually see what open circuit is. Let us say there are n capacitors, C1, C2, all the way till Cn. So what we'll do in step 1, we'll consider C1. When we are considering C1, make all other capacitors open circuit. That is, take all the capacitors from C2, C3 all the way till Cn and make them as open circuit. And then find total resistance seen by C1. Let us say we will call that as Rn1. Then the first time constant, we'll call it as tau 1, will be C1 times Rn1. The next step will be consider C2. In this case, except C2, make all the other capacitors grounded. Open circuit. And then again find the net resistance seen by C2. We will call this as Rn2. We will call this as Rn2. Like this, all the way you can do up till Cn. So here tau 2 will be C2 times R in 2. So again Cn, you can make all the capacitors open circuit except Cn and find the net resistance seen by Cn, which is R in N, which will give you tau N as Cn times R in N. Is that fine? Now, this method states that once you have the idea of all the n number of time constants, the 3 dB angular frequency is given by this 1 by omega 1 plus omega 2 all the way till omega n. I'm sorry, this is not omega, it should be tau. Sorry for the mistake. Tau 1 plus tau 2 is all the way to tau n, where tau 1 till tau n are all the individual time constants. Or I can write this in this form: 1 by summation I going from 1 to capital N tau I, where tau I is the Ci times R in of the ith capacitor. Now, why is this correct? Why is this a good approximation? Why is this a good approximation? The reason lies in the nature of the transfer function. Why can we say that using this formula will give us something that is close to omega of 3 dB? Let us say the transfer function in general is low pass, which is quite correct, and it looks something like this: H0, which is a constant, divided by let us say it's a function of S, so you have 1 plus S by, let us say, some S1 times 1 plus S by some S2 all the way till 1 plus S by Sn. So it's an n pole system. Obviously, when you have n number of capacitors in the circuit, as we just saw, it will be an n pole system in general. So therefore, if I were to now open this bracket in the denominator, what would I see? Let us say I keep the numerator as H0. So the first term will be a product of all the ones, which is 1. Then there will come a term, the first order term, where the S will be common, and over there it will be a harmonic addition of all the coefficients, that is until 1 by Sn. Then we will have the higher order terms, which for the time being we are not concerned about. So once we replace S by j omega, once we replace S with j omega, what will happen? H of j omega will be H0 divided by 1 plus j omega times the whole, that sum from 1 by S1 to 1 by Sn. So let me again write it in the summation form. Sorry, it will be j omega square. So further is for the time being not of our interest. Now let us say when the frequency, the angular frequency is below the omega 3 dB, the second order and upward terms will be kind of negligible, will be so large, or rather they will not play a role in the denominator. So what will happen in this case is that when omega becomes equal to omega 3 dB, when omega becomes equal to omega 3 dB, this and this in magnitude will be equal, because then in that case the gain, the power gain will be 1/2. Okay. So therefore what you can see is that roughly from here you can approximate that the omega 3 dB will actually be equal to this quantity. That is, if the two quantities are now equal, I should say it like this. So using this, I can say that the omega 3 dB will be equal to 1 by summation of 1 by Si. And as you can see for yourself, the Si is the same as tau I, which is the time constant. So therefore this is an approximation which we are using. It's not just an approximation, it's a pretty decent estimate. So now let us see if we can understand this with the means of an example. Let us try to have a closer look at the method of time constants using an example. So let us say I have a Mos amplifier, a common source amplifier, some VDD, I have an RD which is biased for the source, the body is grounded. Let us say I have an impedance over here, Rs, with the source in series. Let's call it as V in, and then the output is taken across a load capacitor CL. Let us say this Rs is 1 kilo ohms, Rd is 2 kilo ohms, the load capacitor CL is 1 picofarad, CGS is 200 femtofarads, CGD is 50 femtofarads. These are given to you as part of the technology. CDB, the drain to bulk capacitance, is 100 femtofarad, and CSB, the source to bulk, is 150 femtofarads. And the transistor is biased in such a way that the GM is 10 milliamperes per volt. 10 milliamperes per volts. So what's the first thing we can do to estimate the bandwidth? We see that both source and body are at ground, so therefore this CSB is not of any use. We can neglect it right away. So the question is, how many capacitors are now there? We have 3 capacitors which are internal to the Mosfet and 1 capacitor which is outside. So therefore there are 4 capacitors. CL, CGS, CGD and CDB. So therefore we are going to have 4 time constants. We'll call it as we'll call it as tau L, tau GS, tau GD, and tau DB. There are 4. So therefore, let us quickly draw the small signal model. Let us quickly draw the small signal model and incorporate all of this. So first thing is V in. We should not miss a single resistance. Then comes the gate. We have CGS. Here is CGD. Then GMVGS. So this voltage is VGS. Then comes RDS. Then comes RD. Then we have the third capacitance, which is CDB. This is the drain. The body is at ground. And finally, we have the load capacitance CL. So let's see one example. Let us say case 1, we take CL. So when we are considering CL, as per the rule, we have to make all of the other capacitors open circuit. That means this and this will all vanish. So therefore, the circuit will be something like this. This is now an open circuit. Then we will have RD, and CDB will also be an open circuit. Here is CL. We have made all the remaining capacitors open circuit. So therefore, we have to see what is the Rin seen by CL. So the resistance that is seen is nothing but the parallel combination of these two resistances. So Rin of L I just forgot to mention in the specification, it's also given that RDS is 2 kilo ohms. So Rn seen by CL is nothing but RD parallel to RDS. So we know that RD is 2 kilo ohms and RDS is also 2 kilo ohms. So therefore this is nothing but 1 kilo ohm. This is nothing but 1 kilo ohm. So therefore the tau L will be CL times RNL, whatever that is. Now when you consider CDB, it is the same case as CL. It will see the same resistance. So if over here also the Rn dB is nothing but RD parallel to RDS, and that is 1 kilo ohm. What about CGS? When you consider CGS, this becomes an open circuit, this becomes an open circuit, this becomes an open circuit. So it's like the right half of the circuit is totally disappeared. So all this capacitor sees is Rs. And that is 1 kilo ohm. For CGD, it is a bit of a challenge. Because it's now not so simple anymore. So the last but not the least, when we consider CGD, so we need to make the others open circuit. So what we will do is we will also deactivate the other sources to calculate the net resistance. So we will deactivate the independent sources. Dependent sources we cannot deactivate so easily. So RS will look like this. Then we have this GM-VGS, RDS and RD. RDS and RD. So it's like saying, what is the net impedance seen by this capacitor? What is the net impedance that is seen by this capacitor? Now to solve this, it's little tricky. We have to approach this in a different problem. So it's like saying, if I connect a voltage source over here, how much current will that draw? So it's like saying, if I connect some voltage source, some Vx, let us say, how much is the current drawn from this source? So it's a little tricky because this is kind of like a floating source. So what we will do, we will make this negative terminal as ground. And what we will do is that the other ground terminals, we will remove the ground and make them as a short circuit. What we are essentially doing is that we are, for our convenience, defining this momentarily as ground and redefining all the other grounds. So therefore it's like saying the source is like this and this is ground. So the RS will be connected over here like this. So even this end of RS must be connected over here. So therefore, this is what I am defining for RS, and the other end that is over here must be ground, and all of these will be like this together. So now the VGS is what? The VGS will now be something like this. Because earlier VGS was like this. Since we had redefined the terminals, now Rx is kind of reversed. This is the gate now. This is the source. And this is the drain. So if this is Vx, we will see how much is the Ix that is drawn. Let's call it as small ix, because it is small signal resistance. So this junction is drawing a current of Ix. So therefore the current that is leaving this junction must also be Ix. So over here, the current that is coming must also be Ix. And I can say that VGS is nothing but minus Ix times Rs because of the sign convention. The current is going from negative to positive, so we are putting a minus. So we can get an expression for Ix. We can get an expression for Ix. How? We can say that Ix is essentially Vx minus this voltage divided by the resistance over here. So if you apply Kirchhoff's law, if you apply the KCL, what you will get is essentially this Ix, part of it is GMVGS and the part of it is going over here in these two. So therefore, this will be GMVGS, this current plus the current in this branch. And in this resistance branch, the current is nothing but the difference of voltages between these 2 points divided by the parallel combination. So this will be this plus Vx minus VGS, because here it is minus, divided by the parallel combination of these two, that is RDS parallel to ID. So if you open this out, you will get what you will get is essentially, just from here you can find out what is Vx by Ix. The solution is pretty straightforward once you have this equation. What you will get is essentially RDS parallel to ID plus RS, that this will come because of the VGS, plus GM RS times RDS parallel to ID. This is the net resistance seen. So the net resistance which it is seeing is RN GD, which is equal to RS plus 1 plus GM RS times RDS parallel to ID. So if you substitute this from the values that you know, or the values that are given, this comes out to be, if I am not wrong, somewhere about 12 kilo ohms. Finally, once we have all the time constants ready, we can simply put them together. So for CL, you will get tau L comes out to be Rn of L times CL. We have this 1 kilo ohm times 1 picofarad, which is 1 nanoseconds. Similarly, for the others, you will get tau dB comes out to be 100 picoseconds. I've already calculated these values for you. Tau GS comes out to be 200 picoseconds, and tau GD, the last one that we did, comes out to be around 600 picoseconds. So therefore, the net summation of all of these, if you add them, comes out to be 1900 picoseconds or 1.9 nanoseconds. So therefore, the omega 3 dB is equal to 1 by this 1.9 into 10 raised to minus 9. So if I take my calculator and punch this in, this comes out to be roughly 526.3 into 10 raised to 6 radians per second. So if you want to convert this into the frequency, that is f3 dB, this is nothing but omega 3 dB divided by 2 pi. So this comes out to be roughly about 84 megahertz. So With this, we have found out, or we have made an estimate of the 3 dB bandwidth of a Mos amplifier circuit using the method of open circuit time constants. So in this particular lecture, we saw how to estimate different figures of merit bandwidth, that is Ft and Fmax, of a Mos device, transistor only. And we also saw one technique, which is the method of open circuit time constants, to estimate the 3 dB bandwidth of a RF Mos amplifier circuit. So we shall continue from this point onwards in the next lecture. Thank you.